There we go. First off, I really want to thank the faculty for giving me this opportunity to come and deliver the Helen Free lecture. Um, just a few words about my interaction with Helen when I was ACS president in 2010. I had the honor and the great pleasure to uh, go to our home in Indiana, and we made a national landmark of where she worked and developed all this important technology that benefited all of us benefit from, and in the process, I got to see just how well loved she was by her community, and how much of the community came out and really supported and celebrated with Helen that great honor of a national landmark being named, for her and her contributions. So for me, giving you this lecture today is very, very special. And I'm going to kind of launch on into some of the stuff we do. And I'm just going to say, before I get off, I kind of think the work we do is kind of cool and fun. And I just say you have some wonderful professors doing atmospheric chemistry here. All of you should go and join their groups. So I'm just going to put in the word here. But so let me go on and get started. In what really intrigued me about atmospheric chemistry is just my imagination went totally wild in terms of thinking about all the possible chemistry that's going on in the atmosphere. There are hundreds or even thousands of reactions that are taking place, both during the daytime and nighttime as well. And just trying to put my own head around the chemistry, it kind of helps if I kind of compartmentalize things a little bit. And this is what I'm trying to do in this slide here, and really trying to take a lot of the reactions and put them in. Well, I'm going to just try to put them in three basic compartments. And I'm only going to look at the reactions that are taking place in the gas phase. And this is how I really started my thinking. And when I look at the three compartments, and I'll start with the first one, which I call first order processes. When I think of reactions that fit into this box, I think of all the reactions that take up a photon from the sun. Once the sun really sun rays start penetrating through our atmosphere, and and molecules will absorb that radiation from the solar spectrum. And one thing that can happen, or actually two things can happen. One, you can get photodissociation, and by photodissociating, you now get reactive entities that are produced. Another thing can happen is that those chemical entities can absorb that radiation and just convert that radiation into heat, and allowing sort of a buildup of heat in particular regions of the atmosphere. That's another talk separate from this one. But once you start getting reactive species produced, as is illustrated here with ozone absorbing UVB radiation, and it photolyzes to oxygen atoms in O2, oxygen atoms can now react with other chemical entities. And so and other species can also react with other chemical entities. So you got two chemical bodies coming together, reacting to create new chemical entities. And so those reactions are called two-body reactions. Two-body reactions are special from a number of perspectives. They can propagate chemistry. They can create new chemical entities that continue more and introduce more reactions. And these are some of the examples. This example here, CH3Br, bromoform plus OH. Bromoform is, how many eat strawberries? Yeah. So out in California, the strawberry farms, in order to kind of prevent bugs from eating, a lot of the farmers spray bromoform and to kind of kill off the bugs. But bromoform goes on up in the atmosphere, and you how we rely on that stuff to be removed in the atmosphere is we use OH radicals. And OH radicals I like to kind of think of as our little atmospheric detergent that just goes up and just cleans up everything. I also like to think of OH radicals in another light. How many of you played Pac-Man and Pac-Lady or Pac-Girl? Yeah. So OH, that little Pac-Man, Pac-Lady just go up and just gobble up creatures, chemical entities, and through these two-body processes. A third category reaction is called three-body reactions. This involves where you have three chemical entities coming together, and these three chemical entities come together to actually form a new species. In the case of how ozone is produced, you got oxygen atoms reacting with O2, and that O2 is so hot in energy that in the atmosphere there's enough N2 and other gases that collide with that hot ozone to remove excess energy, and that stabilizes the ozone. And so this is an importance of that reaction in terms of creating that new species. But these three-body reactions are also known for really taking a lot of reactive intermediates out of the reactive sphere of things, and at nighttime it actually provides a mechanism of really shutting down a lot of reactions that take place during the daytime. Now, interestingly, what we know about the first order reactions, and I'll just come back to that a little bit, from a fundamental chemistry standpoint, there have actually been some Nobel Prizes given out for really exploring the hows and whys photochemistry takes place. And then there have been, Rudy Marcus, for instance, really developed a cool theory along with some others, RKM theory, to really kind of help understand first order processes. Even though Rudy got the Nobel Prize for electron transfer work, but a lot of his fundamental work was in terms of developing really sort of the hows and whys unimolecular processes, which form the basis of understanding photodissociation processes that took place. In about 1986, Yuan Li at Berkeley, Dudley Hirschbach at Harvard, and John Polanyi at University of Toronto actually got Nobel Prizes on understanding the hows and whys two reactive species coming together, how they react or how they don't react, how their structure, electronic structure properties influence their overall reactivity upon a collision. There have not been a Nobel Prize for really looking at these three-body kinds of processes from a fundamental work. So students, there's an opportunity for one of you to get a Nobel Prize, okay, if you want to take a closer look at these kind of processes for really understanding the hows and whys they work. But basically, way we kind of understand how the three-body processes work there are two models out there: the energy transfer model, and what I just recently described to you about how ozone is generated. That's an energy transfer model. So you got oxygen atoms reacting with O2 to give you ozone, which is excited, vibrationally excited, and now you rely upon a third body to kind of remove that excess energy out of it, stabilizing it. So that's known as an energy transfer model. There are a number of groups at Berkeley and Göttingen and Oxford who've actually been working on that model. There's also another mechanism to describe the same chemistry. It's called the chaperone mechanism. And I kind of like to look at this in the way that this is my daughter and this is me, and I'm watching over my daughter, and there's some boy that's been coming around the house asking about homework. Okay, but that ain't gonna happen. But nevertheless, there's some chemistry that takes place. My daughter hates this part of the talk. I'll just let you know. But I'm going to talk a little bit about the chaperone mechanism here, because it's very, very interesting. Now, I put a very simple atmospheric model up here, and all the professors who's doing atmospheric chemistry in the department know this is a very simple model. This looks very complicated, but this is kind of models that we do to say if we know all the chemistry and we know that chemistry very, very well experimentally, and we think we have to be able to describe all the chemical reactions that describe chemical phenomena in the atmosphere. If we run this on out, we should be able to model all the observed abundances that we actually measure. And you can see a lot of interesting reactions. Now I'm gonna pick on one reaction a little bit later. This OH plus HCl. I'm gonna pick on that a little bit. But I also want you to look at this model here and think about what is missing. Okay, I just want you to look at it and think about what is missing. And if you look at it in the sky and see the sky, I want you to kind of think about what is missing. I'm not going to tell you what it is right now, but we're going to come back and it's going to be a little bit obvious. But what I'm going to do is say, I'm not going to look at all those reactions. I'm going to kind of pick on just one or two chemical entities in that atmospheric model, and that is OH radical and HO2 radical. And the reason why I'm going to pick on that is those tend to be two very important species in what are called the Hox family of chemical entities. And the Hox family are very, like I introduced earlier, atmospheric detergent molecules that really help us to clean up the atmosphere very, very naturally. And OH being the most important one. And what generates the OH is that ozone, when it absorbs a UVB photon and produces oxygen atoms, excited oxygen atoms, that reacts with water and you get two OH atoms. And about 80% of the OH radicals that are generated in the atmosphere really comes from this process. These other processes are kind of balances and recycling mechanism that counts for another 10 to 12% of rebalancing back out into the OH. And of course there are some other processes that are minor that contribute to that. And by the way, one of your professors here have been looking at some of those other processes and their significance. Carl has really spent a lot of his time here at Worcester in this group looking at the importance of OH radical reactions here in the atmosphere. But one of the reasons why the Hox family is important, as I say, they're the atmospheric detergent. But a very interesting question came up some years ago. And the question was, with all our man-made activity that's going on and things that are going up into the atmosphere or escaping into the atmosphere, and we're relying upon OH radicals to really start cleaning and breaking things down. With so much activity, the question was, do we have an infinite amount of OH radicals that can continue to clean up? Or is our man-made activity beginning to impact the oxidative capacity of the atmosphere? And that was a big question. And so what a number of people started to do was start looking at the question, well, do we have a handle on today what is the oxidative capacity of the atmosphere? And the answer to that question is really getting a handle on how much OH or HO2 that we have up in the atmosphere. And thus, that triggered a lot of studies some years back trying to get a handle on measurements of OH radicals or HO2 radicals, or the sum of OH and HO2, and even hydrogen atoms as well. And one group that we collaborated with initially on this work was with a group in Kyoto and also University of Tokyo. And and one of the things that they really struggle with their instruments and their measured data is they can never really get the models, the atmospheric models of all the chemistry in those models to agree with what they were measuring. And this is sort of an example of some of the data that really illustrated that if the theory and the model and theoretical results and the measurements were all in agreement, they would be falling smack on this line, and they don't. In fact, what the models are doing is overestimating the HO2, and that kind of implied that there may be some other lost chemistry that was missing. And that sent the community in a frenzy of really trying to identify what that missing chemistry was. Now, in some regards, let me just go back. What some people started to do in really trying to explain some of that missing chemistry, the initial thought was some of these recycling pathways the depth and accuracy of which we knew the kinetics of those measurements perhaps could be retweaked and refined with greater accuracy. And that putting back into the models will help us to refine our understanding of that. And also there was some chemistry with HO2 with NOx compounds that needed to be explored to kind of provide maybe some of that missing avenue of chemistry. That train of thought and exploration was the train of thought of the Harvard group of chemists. Jim Anderson's group of chemistry followed that track. The Caltech group actually followed the track of really trying to look at this recycling pathway, because that had a more direct influence on the Hox balances. So as a result, they went at to try to first off really refine the HO2 self reaction, and of course in the HO2 self reaction, what happens is that will give you hydrogen peroxide, which photolyzes to give you back OH. Okay, and so if they can get a refined measurement that would actually give a better yield of hydrogen peroxide that can recycle back in the HO2, we can resolve a lot of this discrepancy. And so they actually did some measurements. First, looking at the HO2 self-reaction in a very inert environment with argon buffer gas or helium buffer gas, argon being one of the most major inert gases in our atmosphere. But the JPL then did the unthinkable, and the unthinkable was to measure that reaction in the presence of water. Well, why was that unthinkable? And why should it be more thinkable? Okay. Well, if you look up in the sky when you were coming in, what did you see? Clouds. And what are clouds? Water. So there's a lot of water up there. So why hadn't people really looked at this reaction in the presence of water? And that's what they did. They were the first ones to really go back and do that. And when they did, they saw some interesting and unusual things. Now, how many of you are taking freshman chem already? Because I'm going to say something you should know. How many are taking physical chemistry? I'm going to say something you really should know. Okay? So, so here's what the data is saying. So, what this data is showing is that as you add more water, the reaction starts to accelerate. This advancement factor here is really an acceleration factor. So the reaction is starting to accelerate, almost as much as about anywhere between a factor of 5 to a factor of 7 or something like that. But now, as they start lowering the temperature, the reaction starts to accelerate even more, almost getting up to almost a factor of 50. Now that's unusual. And why is that unusual? Well, let's take what we know that you learn from all the chemistry, freshman, organic, physical, whatever chemistry. When you heat up a reaction, what happens? The reaction gets what? Faster. When you lower the temperature, the reaction gets what? Slower. That's what we know. We've been taught that all along. This says when you lower the temperature, the reaction gets faster. And that's counterintuitive to what we know. So what's really going on? So that was kind of a puzzle. So the JPL group said, well, the reason why that's happening is the following. The HO2 sees a water, and now it forms this complex with water. Remember in the chaperone mechanism, A plus M forming AM? And by the act of forming this complex, the water changes the reactivity of the HO2, making it more reactive towards another HO2. So the reactivity of the HO2s are altered from each other by the complexation with the water, and now you get your products. So now that kind of presupposes that an HO2 water complex existed. But the measurements that the JPL group just did the solid measurements looking at the rates by the production of the H2O2. So they didn't have to see an HO2 water complex. They knew what the outcome of the reaction was going to be, and etc. Now that turns out to be important because now, if we take that atmospheric model, and now here's the question, what was missing out of that model? Okay, who's taking Paul's class? For 5 points. No, I can't do that tomorrow. Okay, what's missing out of that model? Did you see any water? Any water in that model? No water. So this atmospheric modeler Stockwell decided to take an atmospheric model that's used to model chemistry in the troposphere, and all those reactions did not have a water effect on any of the reactions, but he put the water effect, that was measured by the HO2 plus HO2 self-reaction to that model, and he calculated out the profiles of species that he saw, and he now compared that with the model without the water and looked at the differences. And that difference kind of give you what is an error that's going to be propagated, with and without the water. And this black mark here kind of defines the errors that he was seeing. So he was actually seeing somewhere between 55 and 70% error down in the chemistry that the models were generating down in the lower region of the atmosphere. And of course, as you go up in the atmosphere, it drops off. And the reason why it drops off because the water vapor profile starts to drop off, and the influence of the water reactions, become minimized. But what it says is that it throws into question how good are those tropospheric models when we don't include the water effect on the reactions in those models in trying to predict out that chemistry. So for us, we were asked by JPL to see if an HO2 water complex exists, and if it exists, what it looked like and where to probe for it. And and this is what my graduate student at Purdue University went off and did. We found some very interesting stuff, some very interesting new fundamental stuff about bonding. Everything we know about hydrogen bonding comes from really looking at water dimer. And water dimers essentially tells us everything about life on this planet, particularly it involves hydrogen bonding. Uh, and, uh, and so in this case here, we're seeing some traditional hydrogen bonding interaction with with the hydrogen of the water with the HO2 terminal oxygen, but we're also seeing a very interesting, unusual, strong hydrogen bonding with the lone pairs of the water and the OH part of the HO2, something about 1.78. But we're also seeing a cooperative double hydrogen bonding effect with a strong and weak motif. This allowed us to really marshal in the new concept of double hydrogen bonding and looking at double hydrogen bonding in atmospheric chemical processes, and that's actually gone more broadly. And I have to say, I need to thank Frank Weinhall at University of Wisconsin, who really kind of helped us to really explore the impact of these double hydrogen bonded systems with water. I'll let you know that they're much stronger hydrogen bond than their closed shell analogs. So in other words, the closed shell analog here of HO2 radical, if I put a hydrogen here, is hydrogen peroxide. And that makes it a closed shell system. And what we're finding is that the radical open shell analog of the closed shell system are actually more stabilized, anywhere from 2 to 5 kcal stronger binding energy than this closed shell counterpart. And well, that's what we found, and what's the actual beef. So actually, Endo at University of Tokyo in 2006 published a paper in Science where he did Fourier transform, FT microwave spectroscopy in the jet on the HO2 water complex. And he also sees this double hydrogen bonded motif in agreement with what we've seen. He also measured the binding energy, which he found to be around 6 kcals for this, and that was consistent with measurements that we also calculations that we had done. There was a group in Sweden, Bernd Nylander, who did some matrix isolation work, and he had actually observed the HO2 water complex in a matrix, and the calculated numbers of what we had calculated, and we were within 3% of his measurements, and that was exciting. Now, my colleagues at JPL said, well, you know, that's kind of fine and dandy, you know, but if we haven't measured it, then it really hasn't been measured. I said, okay. So he said, why don't you send your graduate student over to JPL, and we're gonna go off and measure it. And so Simone, the graduate student who did the calculations, went on, and JPL got on the instrument where they generated HO2 by reaction of F atoms with hydrogen peroxide, and the HO2 was flowed into this white cell where its temperature cooled, and orthogonal to the entrance of the HO2, you bring in water. You now come in with a high resolution FTIR spectrometer, and what you can do is measure these lines. That looks like noise, but I'll let you know that's rotational structure. And we're able to, I didn't say we, I mean Simone did the work, but he was able to assign roughly about 90% of the lines in the spectra to the HO2 nu 3 band. And of course, you can calibrate how much HO2 you have by doing a titration experiment with NO. And so he's producing roughly around 10 to the 14, 10 to the 15 HO2 molecules. And now you know how much HO2 you have, you know how much water you have, you introduce the water. Now you can see the the HO2 lines drop, which means you're losing HO2, but you see new line features coming in, which are due to the HO2 water complex going in. And because you know, like I say, the water, how much HO2 you have, but assuming that all the HO2 goes to HO2 water complex, so you have this loss mechanism, you can calculate equilibrium constant from that. And with that, you can then do a Van Hoff plot of equilibrium constant versus temperature. And these are actually experimental points here, and these one with the bigger error bars are extrapolated experimental points from the experiments at the lower temperatures. And the line here, purple line here, is from ab initio theory, just purely theoretical. Okay? And so now one of the things that our first shock came about. And our first shock was what everybody had missed, was that when you think about in the atmosphere HO2, and you're measuring HO2, so everybody's trying to measure new reactions or refine reactions. But what they're missing is that in the lower region of the atmosphere, the HO2, about 30% of the HO2 is tied up as HO2 water complex. So the instruments are all tuned to OH, or they're tuned to HO2. But if that's all you're measuring, you're missing 30% of the budget. And so now that opened up the question about complexes in the atmosphere and the role of water producing complexes. But it also now opened up questions about now if you're forming these complexes and the complexes are changing the reactivity of the original radical, what does it mean about reactions with complexes in addition to your standard reactions? And this is stuff that work that has actually been further explored. And actually this is a 3D model looking at RO2 complexes being formed in the atmosphere, and particularly trying to understand where they're being formed in the atmosphere. And what a lot of the models are showing, and this is a model done by English group of Dudley Shoalcross, was showing that down in the tropics region, there's significant number of complexes are being formed. And so atmospheric models that are really developed for really understanding chemistry in the northern hemisphere don't really work and apply for really understanding chemistry down in the tropics, because of the significant number of complexes that are being formed that are not accounted for, but whose chemistry are very, very different. And that's been real exciting work. So now it gets to the question, okay, now if you get these complexes, what are their chemical roles? What do they do? How reactive are they? Why is the water changing the reactivity? Does the water really change the reactivity, or is it just a promoter? Okay, these are some of the questions that we started to explore. And we want to explore that taking the simplest system possible. And now I'm going to talk about water-facilitated chemistry. And remember I said, don't worry too much about that model, but there's only one reaction I want you to think about, and that is the OH plus HCl reaction. And and we're going to explore this question with. And the reason why I want to kind of explore, take a crack at this reaction in terms of its significance is that first off, HCl doesn't really break down photolytically down in the troposphere because you don't have the wavelengths to allow that chemistry to take place. So HCl doesn't just photolytically break down. So the HCl, there are two competing processes that go on. One, you either rely on OH to remove the hydrogen, and now by doing that it reintroduces chlorine. Or if this reaction is slow, then the only way to remove HCl is that clouds would take it up and rain it on out. And the general sense is that this reaction is very slow, And so the major removal mechanism for HCl in the atmosphere is clouds taking up the HCl. And this is the experimental measured rates. And the trans configuration here is the more stable. The cis is the more unstable one. Okay, and there's a huge barrier, about 6 kcal, to go from the trans to the cis. But as you bring the gloxal towards the interface, the water starts to catalyze the gloxal. And you actually start to see a distribution of cis and trans. Okay? And now if I can do this right, this is kind of cool. Bear with me. Bear with me. And then we go to the next slide here. So here's the cis. And when the cis hits the interface, it stays at that interface. And if the longer it stays at interface, it will also begin to hydrolyze. Okay? Here's now the trans. And if the trans comes and hits this interface, it hits the top of the interface like the cis, but unlike the cis, it starts to penetrate into the interior. So now the interface starts to select out the cis and the trans. So this is the first evidence of stereoselectivity that cloud interfaces actually will do. We see this also with methyl gloxal as well. And so one of the things we've also have been doing is changing just the solvent to look at the solvent effect on the ratio of cis and trans. And we do see the polarity of the solvent is also very, very important in terms of the kind of ratios that you see in cis and trans. And we can actually flip that ratio by changing polarity of the solvent as well. But keeping it within the atmospheric context, that there is a clear stereoselectivity that we're seeing. And one of the things that now we're also seeing, just some preliminary data, we've been taking some and seeing if interfaces can actually separate out D and L chiral system, and we're seeing some evidence for that as well. So that's been kind of fun and cool. Well, since I'm on here, let me do the following. Oh, what did I do? Okay, you want to see something else that's kind of fun? I have basically 2 minutes, and I just want to make this kind of fun and something unusual. So one of the things that my group has also been kind of exploring is that we ultimately know, like in the case of the the trans gloxal, methyl gloxal, that will ultimately go into the bulk. Just like a whole bunch of other gases go in the bulk and rely upon the rain out to remove them from the atmosphere. But sometimes some winds kind of convect that stuff upward. And what happens to the stuff that's kind of dissolved in it? And this is something that my group has actually been playing around with as well. And one of the systems that we've been looking at is ammonia. So here's ammonia in the bulk of a cloud droplet. And we've actually started freezing it out, because as it goes up in the atmosphere to the lower temperatures are going to start the freezing process. And see what happens when you start that freezing process. Whoa. Well, let's see. I thought we could see. Cannot play media. What? That's too bad. Okay, well, what you'll see is that as the ice starts to form these ice six-membered rings, you would think some of the ammonia would be trapped in here, but actually the freezing process pushes out the ammonia, and and as a result, allows the ammonia to escape. And so now what happens is we have a new transport process for bringing compounds that normally react and are removed down the lower region of the atmosphere to the upper regions of the atmosphere. So everybody, I must bring this to a close. I want to respect the kids. You guys have been real great troopers. No one went to sleep. Some people have been trying to hold out because they have classes. I apologize for running a little bit late. But as you can see, we have a lot of fun doing cool stuff, and we really enjoy what we do. And it's a lot of cool chemistry that we've been discovering. Thank you for your attention, everybody.
Thank you very much. If you need to move on, I completely understand.